Hello, everyone. Thanks a lot for having me here, and thanks a lot to the organizers for organizing this very nice setup in which we can give talks. I'm Soubhik Kumar. I am a postdoc at Berkeley, and today I'll be talking about heavy QCD actions and how it can address the action quality problem and how we can look for such actions. So this will be based on recent work which appeared here with Kevin Kelly from Fermilab and with Zhen from Maryland. So with that, let me get started. So this audience needs no introduction, but very quickly, the action was proposed to address the strong CP problem, which has to do with the fact that why the theta bar parameter of the standard model Lagrangian is so small, whereas you would naively expect it to be some order 1 quantity. So the way the action addresses this is the following. So it says that there is a light pseudoscalar particle, namely the axion, which couples to gluons in this way. And as the QCD effects generate an axion potential, and as the axion relaxes to its minima, the effective theta bar parameter becomes vanishingly small. And that's why it can explain the smallness of the neutron EDM, for example. So that's how it addresses the strong CP problem. And of course, it's a very elegant and minimal from an IR EFT point of view, because all you need is just a single particle talking to gluons in this way. However, when you look at it from the UV, the situation is not so clean. And one way to see that is to realize that we can typically represent the action as a goldstone boson of some Pichet-Quinn scalar, which I'm denoting here phi. And I'm doing a simple representation of the action as a phase of this Pichet-Quinn scalar. Now this guy has a U1 global symmetry, and we typically expect that there will be Planck suppressed or there will be Planck scale violation of global symmetries. And generically, you can write higher dimensional operators of this type. So the idea is that because there's a U1 breaking effect, it will give rise to an axion potential. So along with the QCD generated potential, which I'm writing schematically as this, there will be a Planck suppressed correction to this potential, which I'm writing in this red, coming from these kind of operators, for example. So the crucial point here is, of course, the fact that this cosine and this cosine, they need not be aligned with each other. And if it happens as that this red term is bigger, as is shown here, then what will happen is that instead of localizing to the minima of this black QCD generated potential, the action will generically localize to places like this, which are minima of this part of the potential. So what will happen is that the axion will stop solving the strong CP problem because the effective theta bar parameter is no longer small here, but rather some order 1 number. So what we have seen is that the action can easily spoil this Planck suppressed correction. They can easily spoil the solution to the axion quality problem. It can easily spoil the solution to the strong CP problem. So let's now ask how big these contributions can be. And of course, that depends on how big this parameter FA can be. So we can look at the data and various experimental and terrestrial constraints. They tell us that FA has to be pretty big. And then we see that unless we forbid all operators of this type up to n of 9, these contributions would generally be there, and it would mess up the axion potential. So this is the statement of the axion quality problem. So we basically have to explain why the U1 Pichet-Quinn symmetry is of such a high quality such that we cannot even write down any operator up to n of 9. So the summary so far is the following. Hopefully I have told you that the axion quality problem is a severe one. And if you want to address the strong CP problem, then realistically, the axion quality problem should also be addressed, because otherwise it will just spoil the solution to the strong CP problem. So here, let me just give a very quick outline of one class of models which addresses this. And once again, let's look at the axion potential. So again, here in red, I'm drawing the Planck suppressed correction, and in black, the QCD generated potential. So now the quality problem typically resolves when this red contribution is much bigger than the black contribution, because the axion is localizing in places like this or this. However, if there is any way of enhancing this black potential here, then it can fight better against the red contribution here. So that's the approach we'll take. So we'll ask what kind of mechanisms we can rely on to enhance this black contribution here. And the approach we'll take is we'll basically couple the axion to a mirror QCD sector. And the idea is very simple. We know that the QCD axion potential, we know that in the usual case, the axion potential gets a contribution from QCD. So of course, coupling it to a mirror QCD group can also give rise to a potential. However, the crucial point is that we have to make sure that this new QCD prime generated contribution to the axion potential is aligned with the QCD generated one. And the way we'll do it is we'll impose a Z2 symmetry. So we'll say that along with the standard model matter content and field content, we'll have a mirrored field and matter content. So the idea is that there's a Z2 symmetry that relates everything here to everything in the mirror sector. So there is only one breaking of the Z2 symmetry, and that is done softly via the Higgs parameter, the Higgs mass parameter. So in our sector, we have a Higgs mass, but in the mirror sector, we can have a Higgs mass which can naturally be much, much bigger than our Higgs mass. Okay. So, if we have that, but no other kind of Z2 breaking, in particular, if the same axion talks to the gluons of both the sectors with the same alpha 3 and theta bar parameter, what will happen, as you can see from this expression, is that whenever the axion solves the strong CP problem in one sector, by relaxing into this by making this particular combination vanishingly small, it would automatically solve the strong CP problem in their sector as well. Okay, so there is a single axion that solves the strong CP of both the sector thanks to the Z2. Okay, so however, there is one big benefit of having a large Higgs wave, which is the fact that the mirror quarks are now much heavier after the Higgs prime gets a wave. And as a result, when you run down to low energies, the mirror quarks, they decouple much earlier, and QCD prime runs much faster in the IR. So as a result, the QCD prime confinement scale is now parametrically bigger than the QCD confinement scale, for example. And as a result, you have an axion potential which is parametrically enhanced, but still aligned with the QCD generated potential. And because of this enhancement, it can fight better against the Planck suppressed correction. And that's why we are now less susceptible to the axion quality problem. And here is a benchmark, for example, if you take the Higgs wave to be as big as 10 to the 14 GeV, for example, you can have a mirror QCD confinement scale, which is like around the TeV. And of course, you have the parametric gain in that case over the QCD generated potential. Okay, so I won't have time to explain all of this in super detail, but the idea here is that here we have an IR mechanism to enhance the axion potential. But in principle, if the FA is large enough, you can again have quality problem, or you can also have quality problem from the Z2 breaking through the mirror Higgs wave. Also, in these parts of the parameter space, here, for example, the axion EFT typically breaks down, and also here the axion is typically even lighter than the QCD axion, so our mechanism cannot populate this part of the parameter space. So the summary here is that in these classes of models, there is a large amount of space, but still a sort of compact amount of parameter space that does remain open, where you address both the strong CP and the quality problem. Okay, so now let's ask what kind of experimental constraints we have. And to do that, we'll basically take an EFT-based approach in which we couple the axion to the standard model gauge bosons in this way. But one thing we'll impose is that we'll dominantly rely on the gluon couplings. And the main reason is that we know that the gluon coupling is essential for solving the strong CP. And that's why the C3 coefficient, which characterizes the gluon coupling, will take it to be in this talk, we'll take it to be much bigger than C1 and C2, which characterizes the electroweak gauge boson couplings. In our paper, we do discuss the case where all these coefficients are equal. But for brevity in this talk, I'll focus on the case where this guy is much larger than C1 and C2. And this is also complementary to a lot of existing interesting studies where only photon coupling or W couplings are turned on. Okay, so in this gluon dominant scenario where C3 is dominant, there is still a large number of constraints coming from supernova, cosmology, beam dump experiments, meson decays, and also LHC searches. However, when you put all of them together, you still see a significant part of the parameter space that does remain open. And I should also mention that in this part of the parameter space, we are ruling it out because typically in our case, because of the gluon coupling, you would expect that the Peche-Quinn fermions, for example, they would carry color charge. And of course, there are strong LHC bounds on colored particles. So that rules out this part of the parameter space. But either way, the summary is that we do have this part of the parameter space, which we can try to prove. So here is again the quick summary. So we have addressed both the strong CP and the quality problem. And then we see that there is a large amount of parameter space around the GeV scale. So the question is how we can probe that. So for the rest of the talk, I'll focus on the DUNE experiment, for example, which can be quite useful, as we'll see, as a probe of this GeV scale axions. And before getting into that, I just wanted to briefly mention that there can be quite a few production mechanisms for GeV scale axions. For example, things can, it can be produced through direct glue fusion, although it can be a bit tricky to compute that because of large scale uncertainties. But you can also have production from standard model, pseudoscalar meson, and axion mixing. So we'll discuss both of this in some detail. But again, we can also have axion production from decays, Primakov type production, heavy ion photon fusion, and also axion production in parton shower. But we believe for DUNE, these two production mechanisms would be the important one. And that's what we'll focus on in for now. So here is the schematic of the idea. So we have an intense proton beam with like 120 GeV energy hitting a target. And the idea is that we'll have a standard model pseudoscalar production, and those can oscillate into the axion. And then you can also have direct production of axions from glue fusion. And then once they are produced, they can travel through the rock here, which we have not shown, into the DUNE near detector, where they can decay either into photon pairs or hadron pairs, both of which we will be sensitive to. So the main benefit of using DUNE is that there's a large flux. In particular, the POT is pretty large, which is as much as this, and that's why you can produce a copious amount of pseudoscalar mesons, which can then oscillate into axions. Okay, so let me very quickly mention the kind of production mechanisms we think about. So below a GeV, we mostly focus on this pseudoscalar mixing that we talked about. And this mixing parameters, they can be computed using chiral perturbation theory. Of course, ideally you would like to somehow compute directly the production of a pion-like particle, for example, in these beam dumps. But in this talk and in this paper as well, we have taken this this approach involving chiral perturbation theory as an approximation. For heavier axions, heavier than a GeV, the gluon fusion production would start becoming important. And for more details, I would refer you to our paper. Okay, so that's the production. And then let's think about the decay. And here we are sensitive to both diphoton and hadronic final states. In particular, if you focus on the case of gluon dominance, you see that the lifetime, which is shown in blue, it can typically be pretty large for a decay constant of around PeV or so. We do have a bunch of peaks here coming from the resonances with the pseudoscalar mesons. All right, so let me now very briefly also talk about the backgrounds. So we will have, of course, backgrounds from neutral current pion production or charge current induced pion and muon productions. But the idea is that in DUNE, these backgrounds are typically quite low energy, and also they are pretty isotropic. On the other hand, for our signal, we will have very high energy production, very high energy final states, that is, and we also have the decay products to be quite collimated. So just to show a plot, here again, like for different lifetimes, we are plotting the opening angles of the photon pair, for example, and the energy of the final state. And you typically see that you have large energies and sort of smallish opening angles depending on the lifetime. So that's the main reason why the backgrounds can be handled here. And that's what, and again, for more details, I would refer you to our paper. When you put all of this together, you can then derive the kind of coverage that the DUNE near detector can have. So here I'm showing that with the solid red line here, and you see that especially for sub-GeV actions, it can constrain the quite complementary part of the parameter space, going below the existing constraints, and also complementary to various other proposed experiments, such as the track trigger search at LHC, which we proposed earlier, and along with also Phaser 2, Codex B, Mathus law, and also Na62 for very light masses. So that's the main point here. And let me just very quickly summarize. So hopefully I have told you that the action quality problem is a severe one, and generically it should be addressed while trying to solve the strong CP problem, because otherwise it can spoil the solution. And then we have discussed a class of solutions where both the strong CP and the quality problems are addressed. And then we have seen that the resulting parameter space can be, like some interesting parts of the resulting parameter space can be probed with the DUNE near detector, which is quite complementary to a bunch of existing and upcoming experimental proposals. So that's all for now, and thanks a lot for your attention. Bye.